Hello viewers and welcome to a new STM32 World video. In this video I am going to talk about bit manipulation, in particular a topic called bit banding, which is a feature in STM32 microcontrollers. I have written an article on the STM32 wiki called STM32 bit banding, and you can go and read that article if you want more in-depth information. In order to understand why bit banding is necessary, we have to go back in history. Now, when I was a young engineering student in the late 80s, probably late 80s, we used a microcontroller called 8051, or later named MCS51. But it was an Intel microcontroller. It was an 8-bit microcontroller, and it was severely limited. It could address up to 64 kilobyte of memory, RAM, and 64 kilobyte of program memory. It was actually a Harvard architecture, so you had separate instruction memory and data memory. But we never had that much memory because it was expensive. EEPROMs were expensive, and RAM chips, static RAM chips, were expensive, so we usually got along with like 8 kilobyte or something like that. Anyway, it was a severely limited system, but in order to make it possible to develop applications in such a limited microcontroller, it had some pretty clever instructions. And one of the instructions that I actually remember using quite a lot back in the day were setBit and clear, and one called CPL. SetBit could set a particular bit of a particular port inside the microcontroller, and clear could clear a specific bit. Now the clever thing was that one instruction would manipulate that one bit of the port and ignore the rest, leave the rest wherever they were. Same with the CPL. You could toggle a bit on a port, but you would leave the rest of the bits as they were before you started. STM32 does not have a feature like that, and I'm going to try to explain why that can be a problem. So I have created a new project, as usual, a simple project with a main loop that just prints out a tick where I can play around with things. It does nothing else. So let's try to run it. And you will see that it produces our usual tick output. Now, let's say we want to toggle the LED in this loop. We have done that before. We have used HAL GPIO toggle, but we should look into if we want to try to do this manually. The way we would actually do that is something called read, modify, write. That is the usual method of doing this. So let's try to do this. So first we need to read what is, before we actually go on, let's fire up the STM32 Cube MX, which always start a little bit slow the first time. It might never get there. Happens. It got there. So you see port C have a number of pins it control, and we are using PC13 for the LED. But the output, the GPIO is organized into ports. That will be in another video. I have made that already. And those ports have a 16-bit register which controls the individual up to 16 pins that you could have on that register. So here, if we want to toggle that pin, what we could do is to declare a temporary variable called, let's call it temp, and we read the LED GPU port. The LED have a register called ODR, which is the, if we just do like this, we can see all the registers that we have in this struct, and we can see we have one called ODR, which is output data register. So if we take the ODR value and read that, then we have that stored in temp. Now we can toggle bit 13 on that variable, and the way to do that would be something along this line: temp exclusive OR with a 1 shifted 13 places. And then we take that temporary variable where we toggled 1 bit and we write that back to our output data register. Let's try to run that and see what happens. I have can show that, and there you can see I have the LED is flashing and the value of the output pin is going high, low, high, low, high, low. Now this works pretty well, but the problem with this is that what if all the other pins were used for something else? I don't know what these can be used for. It could be used for an ADC, for example, or it can be used for a number of different things, and we don't want to modify those. Now imagine if this was running and an interrupt happened at exactly this point that modified another bit. We will end up writing a wrong value back to the ODR because we don't have the latest bit. Now, it doesn't really matter how we do this. We could optimize this code. For example, we could do, let's see, we could write a run liner, which would look, I'm copy pasting because I have it already. We could do something like that. It would look exactly the same. We set the ODR equals, but this one, and let's just verify that it's working. There, show the device. What happens if we do it like that? Oh, we can probably leave that running. I won't. So this works as well, but this one, while it looks shorter, it generates exactly the same code as this one. It reads, it just don't create that temp variable, but it still allocates that temp variable internally, or it uses a register temporary for that. It doesn't matter. But it still does the same. It reads the value, it modifies the value, and it writes the value back to the register, and it could still fail. Now we can actually shorten this even further by using some C trickery. So let's, for example, do this, which would do exactly the same, but much shorter written. But again, this code does exactly the same as the long ones. And the problem is that it can be interrupted. It still works. And it can be interrupted. So is there a more clever way of doing this? And yes, there is. STM32 offer a feature called bit banding. As a matter of fact, every single byte in the RAM has a corresponding alias memory address that addresses every single bit. So every byte will have 8 other byte addresses that correspond to each individual bit in that address. That is the concept known as bit banding. And if we look at the article I wrote here, this is all documented in the reference manual, and there is a formula on how you can find these addresses. You also see some addresses defined that are being used. They are defined in what is that? STM32 F45. Let's look at that actually. It is probably down in drivers, hell driver. Is it in the include file? STM32, what was it called? F45. I can do that. I don't know where that is actually, but we could include it. Include STM32 F405XX.h. There, it works. So let's try to open this, and we can search for. It's a little bit slow because it's an enormous file. We search for BB. There. See, we have this peripheral memory map. We have the flash at a certain address. We have the RAM at a certain address. We have the peripheral periph base at a certain address. But then we also have these BB bases. And BB is short for bitband. And using these variables, we can calculate where the bitband address is. So I have created a few macros, and let's copy those macros into the application and define them up here as a private define. We don't need this one anymore. So basically we have a bitband SRAM where we give it an address and a bit, and that will calculate following the formula from the reference manual. Now we can now write a value to, we can use this macro to define an address, and we write to that address, we will toggle an individual bit. And that means we can actually define the LED pin. We could define this as this. We can do it down in the, just before the while loop here. We could define a LED pin, which is pointed to an 8-bit variable, which is using the bitband perif, and it using the ODR and pin number 13 in that ODR. Now, toggling the LED right now becomes almost trivial, because what we can do is down here in our code, we simply set our LED pin equals, well, not LED pin. So basically the reverse of whatever it was. And let's run that. Oh, it runs. Does it work? It works. So what we're doing here is we're using the bitband address of this LED pin to toggle the bit, only that bit. Now the beauty of this is, no matter where an interrupt happens, this line of code here, oh sorry, I forgot to remove this. This line of code will not touch any of the other bits. If the other bits are being modified by an interrupt or whatever, or a timer, it doesn't matter. This will only toggle that one bit in one port. Now, this can be used to do all kinds of things if we want bit manipulation. I played around with this a bit. Let's leave this stuff. But we could also do this with a RAM. Let's see, we have, let's say we have a value, an 8-bit value. We could do that here. Right. And we could also define a const array that have something to cycle around in, and we need a let's do a v counter as well. So what we want to do is we want to write these individual bits into this value. I mean, we could of course just set v equals v values indexed something, but that's not how we want to do it. So what we could do, I mean, this is we want to do it here. So we can write directly into that address, and we can take these individual bits and write them into these the bitbam SRAM, and they will end up in the v variable. Let's wait. What did I want to do? I want to plus the v counter. And if the v counter is bigger than the v values, I cycle it around, right? Because up here I am using the v values v counter, so I cycle through these values, and then let's print out some. Let's change the print statement to actually show these details. I have it, so I don't need to, but I'll explain what I'm doing. So I'll print out the count, which goes from 0 to whatever values we have in this. I will set these values and I'll show the result. I will say the bits is, that is what we are writing into it, and we'll print out the result. So let's try to run this, and it compiled. And let's see what comes out of it. Oh, I didn't. I did. There. So now count will cycle between 1 and, how many do I have? 8. Right. So 1 to 7 is 0 to 7, and then it goes back and it writes these values in. It writes, this is the result, and this is the bits that we actually wrote into 1 bit at a time into this variable. This is of course just a coding exercise, because it's completely pointless because we could just say v equals v values v counter. That would be easier, but it is to demonstrate that we can toggle individual bits in this register using the bitband addressed to where was it? Oh, v, right? It's bitband SRAM as opposed to the bitband perif, which is a different memory region. So that is about it for today. How to manipulate bits in the memory using bit banding, which is a feature the STM32 has, or ARM actually. It's a feature of the ARM Core M0 plus M3, M4. They all have bit banding. It is an optional feature, so it doesn't exist in all ARM processors. I think some of the high-end STM32s, 8.7 or something like that, don't have bit banding because they now have so much memory that it wouldn't be viable to use an address for every single bit in that memory. But on the F0, F1, F4, F3, these features are there in all of them, and it is a very, very convenient feature, and all it takes to use this is 2 macros, which is basically these two. And that is it. Read the article, and please, if you feel that you learned something today, please like this video and subscribe if you want to see my future videos. And I love to hear your comments, so please comment down below. I read all the comments and I do respond. As usual, have a great rest of the day.